Hello. Can everyone hear me?
Yes. Yes, sir, we can hear you.
All right. Hi. Nice to meet all of you. I believe my slot should start in a couple of minutes. Okay. Who is the admin over here? I can't initiate screen share. Oh, okay. Thank you. Okay, I'm not sure if we should just start or are we waiting for any introductions?
Welcome, sir. I think we can start in a minute.
Okay, we'll just give everyone 1 more minute and we'll be on the way.
Greetings everyone. We at SEDSKCT are delighted to present KOSMORENA 2020. Thank you all for your participation. Today is the first talk of the series, Advancements in Space Technology. A small information regarding certificates to the participants. At the end of each talk, feedback forms will be circulated. There are totally 3 talks in this series. Certificates will be awarded only to those who attend all the talks of the series. Please use the registered mail IDs in all feedback forms to avoid any confusions later. So once again, I welcome you all to KOSMORENA 2020. Today's talk will be on the Tesla of Rocketry, revolutionizing space access the Equatorial way. Before we move on to the event, I would like to introduce our honorable guest speaker, Mr. Simongwozdz. I want to make Singapore the space hub of Southeast Asia. These are not just words, but are an expression of a young man's grand vision. He is none other than Mr. Simongwozdz, CEO and founder of Equatorial Space Systems, Singapore. It is an honor to welcome you, sir, and I request you to share your insights and experience with us.
Thank you so much. It's a great pleasure to be here. Thank you for this opportunity. And I'm looking forward to presenting some of our work in front of all of you today. So let me start my screen share. Okay. Alrighty, can everyone see my presentation? Can you folks see it?
Yes, it's
Okay,
visible.
perfect. Thank you so much. So today I want to speak to you about the future of rocketry. But before we go into this, I would like to talk a little bit about the past and how do we arrive at this point and what is really the story behind how Equatorial Space got started, and about the motivation of some of our technological choices, which later became some of our trademarks. So, well, I think, like many people here, I was always interested in space. You can see me, I was probably like 5 years old on this picture. I was obsessed with Apollo 13 with Tom Hanks when I was a kid. I just loved that movie, and if you haven't seen it yet, I highly recommend it. So rocketry has always been with me. It was always one of the things which I always wanted to do. And in 2007, when I moved to Singapore with my family, well, it's a pretty world-famous place for a lot of things, but not for rocketry. And I went through the motions. I went through school, did my 2 years in the military, but unfortunately, I couldn't really do much about rocketry because Singapore is just really, really restrictive. So I had to put my intentions of building rockets, in a bit of a limbo for a couple of years. And when I was in university, I was in the US at the National University of Singapore at that point, I discovered the beauty of hybrid rocketry. So hybrid rocketry is not really a new concept, and it involves liquid oxidizer and solid fuel. So unlike purely solid systems, the beauty of hybrids is that the solid fuel is actually non-explosive. And I decided to start working on some basic prototypes. I mean, not even prototypes, just amateur hobby projects. So you can see on this picture is actually the first, little hybrid which we have built with some friends back during university. And it basically used an acrylic block for solid fuel and gaseous oxidizer for the oxidizer. It was really straightforward. We made it with actual trash just for fun of it. And then we decided to keep moving forward, and we started getting a little more some stuff which was a little more complicated along the way. So at the same time, I basically decided to use my prior contacts since I began to volunteer for the local Space Industry Association to broadcast some of our intentions. And for a very long time, we've been talking about the advantages that launching from near to Singapore could provide. Since we are close to the equator and we have some really attractive areas very close to our city. And well, things started getting more and more serious. I got to present on a number of international events in Singapore and overseas as well, including Europe and United States. The picture on the left was actually when we took the first prize in Dubai back in 2018 for a pitch competition. So that was really a high point. Just an amazing experience working with, speaking with the people from the Dubai.
Okay.
Sorry? Yep, okay. So yes, and moving forward, we decided to start working with liquid oxygen for a while, not very successfully. You can see me wearing this overall here, and there's a liquid oxygen tank behind. And well, because of all this work which we are doing, we attracted the top engineer in hybrid propulsion worldwide, who have just recently moved to Southeast Asia, Jamie Anderson. And since then, we've been making some substantial progress. with very strong technological differentiation, and we are now gearing for launch of our very first hybrid rocket, which is actually slated for late December. So we are keeping busy preparing for the logistics. The test flight will take place in Malaysia. We have been quite affected by the travel restrictions, but we are back on track now after a couple of months, and we are excited indeed. And I can't wait for this rocket to fly. So now let's talk a little bit about the technology, and I want to start by offering you a pretty interesting comparison, between what rocketry can actually become. And the comparison I want to make is actually in terms of automobiles. So if you want to buy yourself a supercar, well, you can choose Bugatti Chiron, which costs $3 million, or you can wait for the new Tesla Roadster, which, surprise, surprise, is actually faster and costs only $250,000. I mean, only, everything is relative. But it's a vehicle with better performances, which is incomparably more affordable compared to the traditional product. And this really boils down to the very simplicity of what Tesla is building, all right? If you look at the engine for a Bugatti, now that thing costs a couple $100,000 to make. It's mind-bogglingly complicated. I mean, there are people way smarter than that I am who can comprehend the engineering that goes into this. But Tesla is very straightforward in comparison. We're talking about 4 electric motors for the drivetrain and a bunch of batteries, and fundamentally that's the majority of the propulsion. And that makes the entire system lighter and, of course, much more simple, much cheaper in comparison, which is why Tesla can build vehicles which are actually cheaper and have even better specifications. And now we plan to do the exact same thing with rocketry, and hybrid propulsion is really the key to that. So now let's take a quick look. I mean, for those of you who are not super well versed with different types of rockets, which I suppose majority of you will have some exposure to it, since it's a space tech discussion. So on one side of the spectrum, we have solid fuel motors, and they can be loaded with a mixture of oxidizer and fuel. Very frequently, it's a composite mixture of hydroxyl terminated polybutadiene and ammonium perchlorate, which is highly explosive, but very straightforward. It doesn't really offer you much control in flight. It is theoretically possible to shut down a solid rocket motor if you have a blow-off valve, which essentially reduces the pressure until it snuffs out the flame. But it's not something that that majority of organizations really have the resources to pull off. They can't be actively throttled in flight, so that makes them only applicable for boost phase operations, basically for the lower stages of rockets, as opposed to most applications of upper stages. And well, while they are simple, they are quite reliable. They are not necessarily cheap. And a great example of a solid fuel based launch vehicle, which is really expensive, is actually Vega from Avio, which is operated by the European Space Agency. Vega is, well, pretty simple. It uses 2 solid stages on a liquid upper stage, and the payload capacity of Vega is around 1.5 tons, and it costs, well, close to what Falcon 9 costs, which has a 20-ton capacity. So solids are straightforward, but they are not necessarily cheap. That is mostly because of the safety considerations in handling of the high-powered explosive. It's really not that straightforward to put something gas generator and a turbo pump to supply oxidizer and fuel into the combustion chamber at the right pressure. Well, the turbo pump itself can cost you $1 million to make if you're cost effective already. So liquid fuel propulsion is more efficient, definitely, because it actually generates higher specific impulse, higher chamber pressures, depending on the types of oxidizer and fuels used. Most commonly, you will see a combination of liquid oxygen and kerosene, or RP1, which is a refined form of kerosene. And well, liquid propulsion does give you this ability to throttle in flight, the authority is really dependent on the design of the flow control system. And most importantly, it can be shut down, and depending on the ignition system design or the fuel and oxidizer types, it can actually be restarted as well. In case of hypergolic oxidizers and fuels, they can be restarted a number of times, which makes them very applicable for flexible operations in deep space. So they are complex, but they are flexible. So, well, you're spending even more money than on most types of solids, but at least it is functional in more than just boost phase. So that is the advantage of liquid fuel rocket engines. On top of this, until it's actually fueled up, and it's practically inert. It's not like it doesn't store. At times tons or even tens of tons of high explosive on its way to the launch pad. Only before launch, it's actually fueled up. So now let's come back to hybrids, which is the third type. So hybrids, again, as I was sharing just now, are not a new idea at all. In fact, the very first example of a hybrid rocket that I could find in literature goes back to 1932. And well, the advantages of using a hybrid were always well known in the industry. The advantages of using non-explosive solid fuel, which by itself is not mixed with the oxidizer. The oxidizer and the fuel are in two separate states of matter, all the way until the combustion actually happens, which makes them very, very, very safe. They are reasonably easy to control in terms of throttle authority and in terms of shutdowns. All you have to do is control the oxidizer flow. Of course, some hybrids will experience difficulties or challenges in terms of the specific impulse impact of the oxidizer to fuel ratio shift on the specific impulse. But in theory, for sake of the argument, they are very easy to control. And unfortunately, the reason why hybrids, despite their obvious advantages, were never practical in space launch operations really boil down to the solid fuel technologies and the chemical composition of solid fuels which were available throughout the decades. And before I jump into that, I just want to give you a quick example of just how safe hybrids are compared to liquid and solid fuel. So what you can see right over here is Falcon 9 back in 2016. Pretty known case, the helium tank, which was used to pressurize the upper stages oxidizer, it came loose. It punctured the liquid oxygen tank, and the whole thing just spontaneously exploded. So you can see the damage, not just it's a catastrophic loss of the vehicle and the payload. It's also a major damage to the launch facility, which was not cheap to put back in service. So even liquid propulsion, with its relative advantages, is still quite an explosive combination. So this example is from 1997, and that is the Delta II. It's a stop motion footage, and you can see that once there is an area of leak forming, well, the explosion is instantaneous. That's what happened, and you can see the loss of the entire vehicle, which is also nearly instantaneous. I believe this mission was loaded with government payloads, and this resulted in loss of $1 billion worth of satellites. So, well, it's not a good thing when a launcher fails. It's not just loss of the rocket, it's also the loss of the payload and the loss of the revenue which this payload could have been generating over a couple of years. So this is an example from the US, the American Rocket Company, or AMROC. That was back in the early 90s. And well, to the best of my knowledge, what happened here is that the liquid oxygen valve was basically froze up. The rocket started to generate only around 20% of thrust, but the guidance navigation control system thought it was already in flight and started to inject hydrogen peroxide for thrust vectoring. This rocket used basically injections of hydrogen peroxide into the nozzle for thrust vectoring. So as a result, it started to burn through some of the insulating liner, and you can see that at this point, this rocket is practically on fire. But you can see the RCS firing up. It's just a complete mess at this point, but it's not exploding. It's like setting a tree on fire. Yes, it will burn up. You have to be careful, but it's not explosive. And this is the great advantage that hybrids have compared to either solid or liquid fuel. In fact, this was easy to avert with just a minor additions to the control systems. And even in this case, when it looks as dramatic as it is, the damage to the launch tower was minimal. It took a couple $1,000s worth of repair costs. So this is really the worst case scenario of what can happen with a hybrid. So now the next question that people usually ask me when I explain to them the advantages of hybrid propulsion is why, if hybrids are really so great and so attractive, then why is not everybody building hybrids all the time? And this really boils down to the fuel composition and their characteristics. So if you take things like HTPB, and if you don't mix it up with oxidizer, what happens then is that the regression rate becomes very, very, very slow. We're looking at maybe 1 millimeter per second at different, depending on the chamber conditions and chamber pressure. So the one method which some companies try to use to overcome that problem, and the example you can see on the left is actually from Lockheed Martin, is use of multiple ports inside of the solid fuel. Port being just the opening in a solid fuel block, which we call grain. So normally you would use just one circular port, but you can do different geometries depending on what you want to achieve with the rocket. And this applies to both solid and hybrid propulsion. So the idea here was that if the oxidizer doesn't burn very fast, then the best way to overcome that problem will be to increase the surface area exposed to combustion by introducing very complicated and very elaborate port geometries, by introducing a lot of ports into this whole system, which was, well, a very sleek solution on paper, but unfortunately that causes a couple of problems. And the first problem, of course, being related to the volumetric efficiency of the entire system. If you introduce a number of ports to a low regression fuel, the first problem you have is the increase in the cross-sectional area of the entire rocket, which induces additional air drag. And another problem is the structural stability. In order to hold this fuel together, you need to implement a support structure inside the solid fuel grain. And that support structure, as you can see on the two images right below, leads to formation of significant slivers of solid fuel. Basically, a bunch of leftover solid fuel, which cannot combust efficiently because of the impeding effect of the support structure, are left behind. And in most cases, you will be experiencing loss to 10 to 15% of your solid fuel to poor combustion. So that's okay if you're building a prototype or a sounding rocket or an academic rocket, but if you're trying to build an orbital launcher, a loss of 10 to 15% of your solid fuel means you will not be able to get into an orbital velocity. So it's a major problem. Of course, there are ways to improve the some companies are now experimenting with 3D printing to remove the excess support structure, but they have not seen much of an improvement in terms of the slivers. So conversely, the other broad methodology of approaching hybrids is by using liquefying fuels such as paraffin wax. And the picture you can see on the right is actually a ground test done by NASA. The Peregrine motor, this was actually built by the Ames Research Center in California. And well, paraffin wax is a pretty attractive fuel because it's very easy to procure, unlike HTPB. HTPB is super easy if you're in the US, not necessarily if you're in Europe or anywhere else. Paraffin wax is pretty much ubiquitous. So paraffin wax was employed a number of times, but unfortunately, the paraffin wax has some problems with it as well. And the first issue is that it doesn't really bond into anything. It's not chemically polar, so it's difficult to hold it in place or properly attach it to the engine housing. And once it's exposed to heating, when basically the combustion begins, you will start to experience very strong slumping effect with paraffin wax. And the slumping effect will lead to loss of geometry, accumulation towards the nozzle, of course, and you will start experiencing mass ejections, which for a different reason, but will still lead to loss of 10 to 15%, in most cases, 10 to 15% of solid fuel to incomplete combustion, which brings us back to square one, and it doesn't really solve the problem. Paraffin wax, of course, can be mixed with other additives, but that will reduce the regression rate, which defeats the entire purpose. It's already not that great. It's around 3 millimeters per second in most documented cases. And on top of this, paraffin wax also shrinks considerably during the curing process, and it therefore requires rotational molding for casting most of the time. And that itself makes it very difficult to mix it with any additional additives, for instance, aluminum powders. And it's basically difficult to mix something with rotational molding and ensure it's actually evenly distributed. So paraffin wax was never really tamed by anybody so far. So this is where we step in. Now, this slide is not the most online presentation friendly, because it really depends on the quality of connection between all of us. But hopefully you will get to appreciate just how stable and nice our combustion is compared to what NASA was doing. So this is one of the test fires which we did quite recently. The thing you can see in the beginning is basically just the ignition sequence, and this is the and for this motor we used liquid room temperature nitrous oxide. And you can see that the flame geometry doesn't vary very much. Hopefully you can see it. It's very nice, it's very even, it's very stable, even with just room temperature nitrous. And because it's at room temperature, you can see that this vapor phase kicks in at the end when the liquid's basically expanded. So conversely, this is what NASA did. I know it sounds pretty crazy comparing ourselves to NASA, but we really have something interesting on our hands. And you can see that paraffin wax is really difficult to combust in any reliable and repeatable manner. In fact, NASA was considering use of a hybrid for the Mars sample return mission, but unfortunately they literally couldn't get it to work with traditional fuels, and they replaced that with solid propulsion at the end of the and just launched that. So now let's look a little bit more. This is another firing. Let's talk about the benefits of HRF1. So we have regression rates higher than 4 millimeters per second, which is 4 times what HTPB produces at similar chamber pressures. And as a result, we can get away with using a single port. So it makes it structurally stable without using any additional support structures. So the sliver that we've experienced so far is below 4%. We are confident we can bring it down to 2%, which at that point will be very competitive with even liquid propulsion in terms of total efficiency. Depending on the oxidizer delivery system that we use, we can achieve between 240 and 250 seconds of specific impulse at sea level, and north of 300 seconds in vacuum, which also makes it competitive with Kerolox. And it's twice as dense as paraffin wax. And so our proprietary solid fuel is really the solution to why hybrids were never competitive with traditional propulsion systems. And that unlocks an immense economic, commercial and scientific potential. So now, how much do we get with our technology for 120,000 US? So on the left, you can see the Rutherford engine, which is used by Rocket Lab in the Electron vehicle. So they've already done a very, very good job reducing costs, because instead of using an open power cycle, they decided to use an electric pump to deliver oxidizer and fuel into the combustion chamber, which is really an amazing piece of technology. And from the publicly available information, we estimate that it probably costs around 120,000 US to manufacture each one of those. In our case, for the H750 motor, which is currently under development, which will be used in the orbital class launcher that we are developing, it will basically be very similar in terms of the price per unit, but we'll get 3.3 times the thrust out of it, which means we only need to use 4 of those for the launcher as opposed to 9. And that's the kind of price savings that we can achieve thanks to our technology. So now moving forward, of course, we do have some ambitions to work on heavier launch systems. And what you can see here is the Merlin from SpaceX, which is a very extreme case of complexity in modern rocketry. But with our propulsion technology, we estimate that we can build something of similar thrust for $500,000, which is, again, around 1/3 of what SpaceX is spending. And the functionality in terms of even power descent capability is actually still there. So we could make our technology equally reusable and even at a much lower baseline manufacturing costs. So now, what are we planning to build with this? So we are developing this orbital class launcher, which we call the Volans, and it's going to go into the exact same market niche as the Electron. So Electron is, of course, as we all know, a liquid propelled rocket. It uses LOX and RP1. And based on what Peter Beck was saying, it cost them $120 million to develop. And the price per launch is around $6 million US right now. That's the list published price. I believe they charge some clients much more than that. In our case, we're looking at development costs, which is basically 1/4 of what Rocket Lab had to spend. And we are confident in that because, well, very simple reason, we avoid use of cryogenic oxidizers. Moving forward, we'll be using nitrous oxide at a chilled down temperature at -60 degrees. At that temperature, nitrous oxide is equally dense as liquid oxygen, but -60 degrees is still a temperature regime which is very comfortable for most engineering plastics and composites to handle as compared to liquid oxygen. If you've ever built any supply systems for any form of cryogenic piece of technology, you will know that cryogenic rated flow control systems are really expensive. A good example would be a flow control valve I saw once, which was rated for aerospace use, and it cost close to 15,000 US. In our case, we get away with stuff which costs maybe a few thousand US. Also, the delivery system that we are developing for the Volans will use some of the natural effects of nitrous oxide instead of having an open cycle, which by itself is going to reduce the cost and complexity considerably compared to even the Electron and the Rutherford engine. So this is really what gives us the confidence in being able to complete this program at a record low cost, at a record speed. So even though you can see that the price is not super lower compared to the Electron, we're looking at having a pretty healthy profit margin out of this system as well, which is important from the business point of view. So let's come back to Earth for a second. Okay, so we did not invent we did not invent the hybrid rocket motor. We do not make that claim. Just the same way that Tesla did not invent the electric car. In fact, electric cars have been around since the 19th century, and they were trying to compete with internal combustion engine-based vehicles, but they were unable to because of the battery technology. Batteries were simply not energy dense enough until quite recently. And that was why, even though everybody understood the benefits of going with an electric car because of how simple it could be, it was not really possible to build one which was competitive with anything else in the market until now. And this exact same thing applies to us. And HRF1 is to hybrid rocketry what lithium-ion batteries are to electric vehicles. It's the missing piece of the puzzle which we have provided, and thanks to it, we are now able to unleash the immense potential of hybrid propulsion into the world. So moving forward, I'm really excited to announce that this small vehicle, which will be the very first in-flight application of HRF1 after close to 12 years in development of the solid fuel technology, it will be ready for flight by December this year. Well, I prefer not to disclose the exact date because that might still change depending on the weather conditions. But it's been really challenging to arrange that test flight in the first place. So we're really happy that it's finally happening. It will take place in Malaysia. Of course, Singapore as a city-state is not the best place to be doing any sort of launch. So we had to navigate quite a bit about the travel restrictions, and this is really the reason why we had so many delays this year. And it just feels awesome to be finally back on track. And moving forward, we'll be building our suborbital rocket. The design is already complete. We are currently fundraising for the development flights of this Dorado rocket. And the interesting thing about Dorado is that it will actually contain 0 pyrotechnics at all. not only our solid fuel will not be explosive, as it already is, but rather even the payload separation and the staging systems will also be pressure-based. So they will not depend on any form of pyrotechnic devices. That will make it the safest suborbital rocket ever built anywhere in the world. And it will also be using our proprietary solid fuel, of course. It will be using chilled nitrous oxide at minus 60 degrees centigrade. And as a result, with solid fuel, which is twice as dense as paraffin wax, and with oxidizer, which is as dense as liquid oxygen, we really pack a lot of energy in that system, and we do it safer than anybody else. The two different versions of that, the single and the two-stage versions, will be capable of reaching 105 and 270 kilometers respectively. And we are looking at payload capacity of 25 kilograms, which will make it ideal for academic and scientific payloads. And of course, moving forward, we'll be working on the volans, which will be, well, way bigger. I can't wait to get started on that. It's just going to be, beautiful to be doing ground testing on 80 kilonewton motors. I'm really looking forward to that. The payload capacity you can see over here, that's for a 600 kilometer sun-synchronous orbit, which is really the reference point we are going for. But this is the worst case scenario. So most likely we'll be looking at closer to 150 kilograms of payload to 600 kilometers sun-synchronous, which is going to reduce the cost per kilogram massively. Also, thanks to our location, we are looking at launching into a variety of different orbital inclinations. Right now, the options for near equatorial orbits are pretty limited. Majority of small launch system developers are focused on polar and sun-synchronous orbits, and we do see a growing market interest for equatorial low Earth orbit, and that's one of the market niches we want to jump into. And it's made possible by operating from locations which are very close to the equator. So we would not be experiencing significant penalty in terms of the dogleg maneuver, depending on the launch site, or we would not be experiencing a drastic plane adjustment maneuver penalties. So it's really the full package which we can provide. It's a vehicle which is safer, more flexible, and more affordable compared to anything available in the market. So if you'd like to get involved, we are not hiring right now, but please do drop by our website. Drop us your CV at careers@equatorialspace.com. And we would like to stay in touch with you. We do keep track of every applicant. And when there is an opening, rest assured, we will be looking at all of the applications. So hopefully that will give you some, hopefully this really answers, most of the potential questions about what are we working on. So thank you for your kind attention. Alrighty, so let me just open up the chat and see if there is any questions. Right, it's loading, just a while, please. So sorry, Prisha, how much time do we have for the Q&A?
Sir, we can take, it depends on the number of questions. We have time.
Alrighty, sure. I'll do as much as I can. Alrighty, please, okay, who can apply for internships? So generally, for internships, we currently look mostly at people based in Singapore for practical reasons, but we don't have any firm restrictions. So this is unlike, for instance, the US, which has deemed export rules. We don't have that problem in Singapore. So, well, we are quite open in that sense. In terms of backgrounds that we are mostly looking at, well, we need hardware development engineers, electrical and electronic engineers, of course, aerospace, propulsion, structures and mechanical, and we are moving towards manufacturing. So we're also looking for people with at least some exposure or experience to factory management and manufacturing. Yeah, we don't have a very specific position open right now. So basically, that's it. Hopefully, this answers your question, Grishma. So, Sid, does electric propulsion produce less thrust? Yes, electric propulsion is very, I mean, it's not my area of expertise at all. I know one guy in Singapore who is very good at electric propulsion, but I will try to answer this to the best of my ability. So, of course, electric propulsion allows for much higher exhaust gas velocities. We're looking, and therefore higher specific impulse. But unfortunately, the problem with this is basically there is, I mean, electric thrust doesn't produce, electric propulsion doesn't produce a lot of thrust, and therefore it's not really practical for launch applications. It's great for station keeping or for long-term maneuvers in space, but when you're actually getting into orbit, electric thrust is simply not good enough. The thrust-to-weight ratios are nowhere near what you require. Okay, what's the diameter of the rocket? So for the Dorado, the suborbital rocket will have around 31 centimeters in diameter. The Volans launch vehicle will have 2 meters. Will have a diameter of 2 meters at the booster. Okay, do we plan to work with plasma propulsion at some time? We don't have the resources to do 2 concurrent programs right now. So we don't have any plans. We would like to diversify into exotic propulsion once we have more resources, which is to say in the next 5 years when our launch operations are well established and generate enough profit. What software? Okay, that's a really good question. So we use ANSYS a lot, and we use Inventor and well, SolidWorks. A lot of our engineers use SolidWorks. For things like mission analysis and launch trajectory analysis, we use Astos and STK. So those are pretty much the industry standard. And well, they are pretty expensive, but yeah, it's some academic institutions might have them. Not sure how about yours, but maybe it's worth a check with some of your professors if there is access to them. Okay, how about using nuclear energy for engines? Well, I'm a huge fan of nuclear propulsion. I think the potential in that is immense. There are some challenges regarding that, and one of them is reliability of launch systems. If you want to put, several hundred kilograms of uranium at 3 to 4% purity, which is good enough to propel an electric, a nuclear thermal rocket. You have to have a really, really reliable launch system, and at this point, the average launch failure rate still remains close to 6% across the board. So I think that's one of the major deterrents to applications of nuclear propulsion in space. So yes, I think the potential in that is very good. I think it can provide a substantial thrust-to-weight ratio and at twice the specific impulse of chemical rocket propulsion, just like Nerva did back in the 60s. And I think I would love to see some of applications of that stuff in space operations in the near future. But that's basically all I know about this. It's also unfortunately not my particular area of expertise. Okay, so what exactly do we use? Okay, Rishikesh. So any plans for reusability in the near future? Yes, it's possible. Okay, so it's possible to do that. One of the options that we have explored is quite similar to what Rocket Lab is doing with a parachute recovery and a helicopter. It's not a new idea either. In fact, to the best of my knowledge, it's been done since the 1960s with spy satellites, which did not actually stream down any of the imagery, and they were actually captured during descent on a parachute. So that's one of the options. For small launch vehicles, having a powered descent will sacrifice so much payload capacity. Doesn't really make much of a sense, especially when it comes to launchers which are which have such small payload capacity as what we do, and which are so straightforward to manufacture. It's just easier to mass produce them. So we don't really think, we're not very serious about reusability for Volans, but moving forward, once we start working on mid-size launchers with maybe 2 to 3 ton capacity, at that point it already starts making a lot of sense. So it's possible to do a power descent with a system of that sort, with a hybrid. So that's basically, yeah, it's a possibility. It's something which we have to do a more in-depth cost-benefit analysis before we actually implement that. Okay. Okay, so what exactly do we use as fuels? Okay, so that really depends on the mission application. So let's focus purely on chemical rocket engines, all right, or motors. Let's not talk about electric or nuclear, just chemical. So for liquid propulsion, there are two broad categories of liquid of fuels and oxidizers. One is so-called non-hypergolic and one is hypergolic. So hypergolic just means that it ignites spontaneously on contact with one another. And hydrazine, unsymmetrical, dimethyl hydrazine, those are some examples of hypergolic propellants. They are very well, corrosive and carcinogenic, not very safe to handle. They are inherently toxic. So that's the drawback of using hypergols. But hypergols are also stable in at room temperature, and therefore they can be stored inside of the tanks for extended periods of time, which makes them very useful for long-term missions. If you're sending a probe to Jupiter and 18 or 20 months later you need to ignite its engine, probably a couple of times because of the mid-course corrections, and still have enough fuel on board to make sure that you're actually injecting yourself into the orbit around it, then you definitely want to use a hypergol at this point. That's just the fact that you don't need any external source of ignition is, and the fact that you can store it in your tanks for a long period of time is just the winning combination. For most launchers, liquid oxygen and kerosene seems to be the most common combination, especially among the small launchers. There's over 100 different companies discussing development of small launch vehicles right now. Vast majority of them are liquid propelled, and LOX and kerosene seems to be like the most common combination right now. And that's a non-hypergolic cryogenic combination, which is more efficient in terms of specific impulse, but it requires an external source of ignition, and liquid oxygen does vent over time. So it's not the best option for long-term missions. All right, so do we have plans to increase the second stage size and increase payload size? Not right now, it's possible. In fact, one of the ways to go about this in general will be by implementing structural connectors for basically to attach 2 or 3 boosters coaxially. So that's one of the options that we are discussing, which would be practical for increase of the payload capacity without actually developing a whole new rocket system. So yes, do we charge any fee a month for internship? Okay, I can promise you we'll never be charging anybody for internship. Okay, we may not be able to pay. We are still running with pretty modest amount of resources, but I don't think anybody sane would ever expect an intern to pay them. I think that would be pretty crazy. So no, definitely we won't be charging anybody anything. What is my opinion about Project Skylon? Okay, very interesting. I think if reaction engines works out this pre-cooler technology, which might require a couple of extra years for material science to really catch up to the requirements, I think it might be a game changer. But that said, I'm confident that it will still take them maybe a decade before they get to that point. And in the meantime, we have to address the huge demand for small satellite launch, which is why we are still doing what we do. But I'm keeping my eye on reaction engines. I think it's really, really quite exciting what they are working on. Okay, what is hot staging? Okay, so in certain kinds of rockets, when you don't have a pressurizing system, but you rely on the inertia of the fuel flowing into the feed lines. Now, there is a certain point when you shut down your engine when this inertia basically just starts to go all over the place. You will stop intaking oxidizer and fuel, or just oxidizer in case of hybrids, into the combustion chamber, right? So one way is, so basically there are 2 broad categories of solutions to solve that problem. For again, for non-pressure fed systems, those are different. Okay, you have drift staging, which Americans were using a lot back in, Saturn V was using drift staging, for instance. And the way to do that was, once you start experiencing this inertia, Basically, they would activate those smaller solid rocket motors on the side of the rocket just to produce a little forward acceleration, let the propellant and the oxidizer settle on the feed lines, and only then the main engines would actually kick in. So that's drift staging. Hot staging is a little different, and that was favored by Russians, I mean Soviets, and now the Russians. And that essentially involves activating the second stage engine before the first stage is actually off. So you never experience that ullage effect. It's technically known as ullage. You know, this entire effect of vapors mixing with liquids when acceleration, basically in free fall, when acceleration ceases for some time. So yes, that's what hot staging means. Of course, you need to have this truss interstage because you will ignite that thing before you actually separate from the previous stage. And well, the only it's working pretty well. I know Soyuz still uses hot staging, and it seems to be doing very, very well. Okay, Sunil, will there be any recruitment for materials engineer in your company in the near future? Most likely, yes. Material engineering and structures engineering is definitely an area of major focus for us. Not right now, but it will become so in the next couple of months to maybe a year or so. Okay, Rishikesh, thank you so much. And do we have online internship for students? No, we don't right now, but that's a pretty interesting idea. Okay, another from YouTube Live. Is rocket plastic free? I'm not sure what is plastic in this context, but okay, let me try to answer this the best way I can. So some hybrids can be using plastics for fuels. Well, they are not free, but they are very cheap. So yeah, hopefully this is the right context. I apologize if it's not. Okay, for any opening for aerospace engineers, again, we are not hiring right now, but please do drop us your CVs because once we close the next round of funding, we'll definitely be expanding our crew. Are nozzles 3D printed? Okay, at this point, we use graphite nozzles, which are just machined. It's possible to 3D print them, but at this point, we don't really see much of a point to do so. Again, 3D printing would be particularly valuable for regeneratively cooled nozzles, which use cryogenic oxidizers to basically just run through the bell to actively chill it down. In our case, we don't use that. We use passive cooling, which means that we don't really need to work on that. Not at this point yet. Okay, what are the options for greenhouse gas-free rockets? Okay, wow, that would be really difficult to achieve because even water vapor is technically a greenhouse gas according to some definitions, and certainly carbon dioxide is, which is a product of, well, most combustion processes. I think a bigger issue with rocketry is not really the amount of carbon, of greenhouse gases, because again, rocket launches, even with the increasing frequency, are generating just a small, tiny percentage of the total global emissions. I think a bigger problem is toxicity of certain oxidizers, especially ammonium perchlorate, which is notorious for polluting groundwater around launch sites, and it's probably a bigger environmental problem to worry about. Okay, moving forward. Recently, a researcher claimed that he can accelerate us to extremely high speed using Mega Drive, which he invented, but the chances of reaching that speed is 1 in a million. But he says that the engines are capable of thrusting to highest speeds achieved till now. What are your views on this? Again, I am not an expert in novel and exotic propulsion technologies. I never heard about this project, so I don't think I'm really capable to answer this, any more than this. Certainly, if somebody figures out, means to improve our transportation, that would be a very good development for entire humanity. That's really all I can comment on this right now. Okay, which is best fuel, sugar or N2? Okay, so I believe this pertains to sugar rockets. Well, again, we kind of missed a step over there, and we just went straight to our proprietary propulsion. So probably not the best person to really answer that in context of amateur rocketry. So sorry, Bharat, but that's just the reality. How is the course of a rocket corrected in the lower space boundary? Is there any special fuel tank that is induced in the rocket for this? Okay, so for the two lower stages, we'll be using a thrust vectoring system. So it will just redirect, the exhaust gas by a few degrees depending on the required maneuver. We do plan to implement an RCS for the third stage and the final stage, and for that we will basically have a separate tank for. Okay, we might have a separate oxidizer tank, but depending on our trade-off analysis, we might just use nitrous oxide coming from the main tank and run it through a catalyst pack to increase basically the specific impulse from use it essentially as a monopropellant for RCS. It's another option that we are looking into very seriously. So in this case, we will not actually have additional tank. So yeah, hopefully this answers it. What are we specifically planning to do? Of course, it really depends on the design considerations of every individual program. Okay, how to apply for an internship? So at this point, we don't have an internship program per se, but please do drop us an email to careers@equatorialspace.com. If you have a CV, please attach it alongside with it. You can just drop us a couple of lines, like what is your background and what would you like to accomplish? Are you looking for a full-time job, or are you looking for an internship, or are you looking for an advisory position or anything of that sort? That's especially for any senior engineers who might be watching this. So yes, please just reach out to us, and we have a spreadsheet with everybody who contacted us. So even though we are not hiring right now, or we are not opening up for any internship programs, we will definitely be looking into that in the near future. So okay, so kerosene and oxygen are used for space rocket. Okay, can you explain that? I mean, yeah. So basically, you need oxygen in some form to maintain combustion, and you need fuel to maintain combustion. So that's unlike just very much the same way as every other rocket, or anytime something's on fire, you need those three things. You need oxygen, fuel, and heat. So well, of course. So that's actually a pretty interesting thing. If you were running pure gaseous oxidizer, like just pure oxygen, you would actually have a much higher degree of mixing of the fuel and oxidizer. You would actually have a higher efficiency. But unfortunately, gaseous oxygen is really thin. There is not much of it per unit of space, and the most efficient way to store it is by using liquid oxygen, really, because that's just the densest. And in a rocket, you want to put as much energy density as you can in a very confined space. So that's why liquid oxygen is commonly used. And basically, the job of a well-designed injector is to make sure that it spreads out and atomizes as much as possible and becomes as close to a pure gas as possible for a more efficient combustion. So that's basically it. And it just happens so that kerosene and oxygen are very common because the entire supply chain in a couple of countries is based on that. There's just been a lot of heritage building propulsion system that uses specifically those two. That now, when a new company steps in, it's just very natural for them to build that. So it's really a matter of heritage and what people got accustomed with. Of course, it's not the only combination which can be used for liquid propulsion technology. There's many different fuel and oxidizer options, and in fact, some companies are actually innovating in that sense in some really interesting directions. So why can't we use sugar in rocket fuel? Okay, we can, but sugar, again, the specific impulse you get from a candy rocket is just not good enough to be practical for any actual launch applications. So once you are building an orbital launcher or even a sounding rocket, you need to use something that basically packs more energy. That's more explosive in case of in terms of like solid propulsion. Okay, will Starling end up dominating exospace? Okay, I don't think Starling will dominate completely. I mean, so there are two ways to answer this question. So will megaconstellations really dominate low Earth orbit? Yes, they will. Not altogether, because all spacefaring countries are currently discussing ways to manage, the traffic situation, and this pops up at every single conference I go for. There's at least a couple of discussions going on about the orbital slot management. So in that sense, it will not be the only constellation that's present, but definitely there will be a lot of satellites forming mega constellations. From the other perspective, which is slightly lower level perspective, I don't think every country will sign up to be a part of Starlink because, for the same reason that they have their own telcos. It's a strategic industry that you don't necessarily want to delegate to an overseas entity. So I think it's actually quite interesting, but I think a number of countries and their allies will be using their own networks of satellite broadband in the near future. I don't think everyone is going to just sign up for Starlink and start issuing licenses for ground stations for Starlink. I don't think that's going to happen. It's just too sensitive for too many countries who want to control their own telecommunication networks. Okay. However, is change of orbits? That's one of my favorite questions and subjects, in fact. So at LEO, and we were talking 400 to 500 kilometers altitudes, if you want to adjust your inclination by 10 degrees, well, you're looking at roughly 1.4 kilometers per second of delta V. So if you want to adjust it by 30 degrees, well, do your math, that's over 6 kilometers per second. That's almost as much as what you need to get yourself into orbit in the first place. So changing either your inclination or changing your local time at ascending node, which essentially reorientates the orbit, requires a lot of propellant. The delta V's budgets are very much against doing any maneuvers in low Earth orbit. And that is the exact same, the very reason why geostationary satellites only do their plane adjustments when they actually get to the highest point, close to apogee, which is at that point basically the penalty is the lowest because they don't have to correct their because at the end of the day, plane adjustment is a sine function of your velocity, of your horizontal velocity. So that's the most efficient way. That's one of the reasons which I believe dedicated launch and not space tugs will be preferred for different inclination options for low Earth orbit. Of course, when it comes to space tugs and deployment from LEO to GEO, I think that's a much more practical option in terms of the delta V budget. Okay, hopefully this gives you some of my thoughts, Ramesh. Okay, Sanjay. What do you generally expect from an aerospace engineering graduate? Okay, what we really like seeing is people who have hands-on experience on doing on building hardware. So yes, if you have any portfolio in terms of your projects, whether in school or outside, that's something which we really like to see, because very often we end up troubleshooting on the spot. So that's a very, very valuable ability to have for our people. Okay, what exactly is the factor for opting hybrid? Really, the safety and the fact that we could get the necessary supplies to build those things without getting a police permit, without dealing with explosive licenses, which again in Singapore are borderline impossible to get for someone who's not a major company specializing in pyrotechnics. So that's really that was really the factor why we started. But in the end, we have developed our technology and we roped in the right talent who essentially brought the expertise to bring this into a commercial success. Okay, internships for computer science and engineering students. Again, so ditto as for all kinds of internships. Not right now, but do drop us your CV. We do have computer science and computer engineering people on board. Yes, we do. There's quite a lot of software engineering, especially to going into rockets. So Sunil, why did we use hybrids instead of liquid? Yes, so that really boils down to the cost. It's really not cheap to build a liquid propelled rocket, even if you're just using a pressure fed system. I know some amateurs in the US did that. But even a basic one will cost them a couple tens of thousands of dollars in with all the supplies required. So it's just much more expensive. And we didn't feel like this was in the early stages. We didn't think that was a very practical way to go about this. Okay, what skills should we possess as electronics students to join the aerospace race? So that's really comparable to what I said about the aerospace engineering students. Hands-on experience putting stuff together, troubleshooting, and fixing stuff on the fly, and improvising. That's just the most important consideration that we usually look at. Okay, does aerodynamics play a role in propulsion? Well, partially in propulsion, but definitely in rocketry as a whole, yes, because you need to design your rocket in a sense that it's, depending on the mission profile, stable, and that you need to incorporate the effects of, even the plume and the plume dynamics into the models for guidance navigation control systems. So yes, aerodynamics are very relevant. In fact, they are critical for rockets because we are traveling at pretty high velocities, and even in the lower parts of the atmosphere, when the rocket is still somewhat slower, the forces can be really brutal. So it is very important for any rocket to be well designed from the aerodynamic perspective. Okay. So what? So Adarsh, so nitrous oxide and hydrazine as fuel, which one is more efficient? Okay, so nitrous is useful as oxidizer, not fuel. But compared to hydrazine, well, it doesn't kill you if it leaks. That's basically the advantage of doing that. In terms of specific impulse, I think hydrazine will be slightly better. Slightly, I don't think there is a huge differential actually. But yeah, nitrous oxide has some disadvantages as well, especially that at 36 degrees centigrade it basically goes supercritical, which is not great. But in general, it's a much safer choice compared to hydrazine. Hydrazine is notoriously carcinogenic. Nitrous oxide isn't. So yes, it's not just a matter of it's a matter of a holistic approach really. When it comes to design, you have to not just look at the specifications of particular combinations, but also at the operational considerations. What is actually the better choice altogether from multiple different perspectives, including things like specific impulse, volumetric density, energy density, and of course the safe handling characteristics. Okay, so I've got to run soon, so sorry guys, but this will be the very last question. Okay, maybe second last. Any book suggestions to read about rocketry? So Saturn, definitely, Rocket Propulsion Elements. It's just the Bible of rocketry. Everyone goes for it, and it will give you a very, very strong introduction into the entire field. I've read it myself, and it doesn't contain a lot about hybrids, unfortunately, but it's just the most comprehensive introductory text you can never ask for. And okay, so Sai, what type of feed system and power cycle do you use in hybrid rocket engines? Okay, so that really depends. Most of them are actually pressure fed, so you can pressure feed it with helium. That's what we plan to do for the suborbital rocket. And again, it's comparatively lighter because we don't have to pressurize two different tanks. And with one tank, that's basically half of the mass that has to be incorporated into the system, because pressurized tanks are typically thicker and therefore heavier compared to the ones we use in open or closed combustion cycles, but basically anything using a pump or a turbo pump. So in case of hybrids, use of pressurized systems is just more practical compared to like boosters in using liquid propulsion, because the mass penalty is not that big. And on top of this, I can also share that we are developing a novel kind of oxidizer delivery system for the Volant launch vehicle. And well, it's really just a teaser because I'm not able to disclose anything more about that, but I can only share it's going to be very simple, and it will supply chamber pressure, well, at more than 60 or 70 bars. So at those chamber pressures will be competitive with cryogenic propulsion in terms of specific impulse. So that's another piece of innovation we are working on. Okay, everybody, thank you so much. I really have to run now. So yeah, hopefully this answers, I know not all of the questions, but enough questions. And Yeah, once again, thank you so much for the opportunity to present in front of you today. It's been a great fun. And do drop us your CVs if you're interested in staying in touch. And I promise you that we will be keeping track of every single one of them.
Okay, sir. Thank you for the insightful session. I, on behalf of SEDSKCT, our entire crew behind the event, take pleasure in extending our gratitude to the speaker, Mr. Simon, and all the audience who graced the event in great numbers. A big thank you to you, sir, for an amazing and insightful session and for spending your valuable time with us. Thank you all and have a great day.
Thank you so much for having me, and same to you. Have a great day, everybody. All right. Cheers. Bye-bye.
Bye. Participants, please fill the feedback form given in the chat box.